Iwe, nakutana mwenye mchana. Tekini nimendi. Hapa, mwenye. Wache tukae nayo business. What? Ah. Yeah, police. Right? Student. No, watu wakumbuka. Hapa. Unataka kumbuka kitabu. Nabatika hapa. This too. Moise. Ndio punzi. Basi.
To get my
and together we take responsibility for not helping the body of Christ mature.
Okay, so we can start our tutorial. I'm seeing people are joining now. So I think we can give them a few seconds so that just a minute, so that we see how many people will join after a minute. Then we proceed into the tutorial. Okay, I think we can start now. Are we able to see the screen and get the audio?
Yes, we can.
Okay, thank you. Hope everyone's okay. Our topic for discussion is chemical bonding. So we're discussing chemistry, and in chemistry we'll discuss chemical bonding. This one needs to be very interactive. Wherever we are not clear, wherever you need to clarify something, make sure you do so quickly. Okay. So chemical bonding. Okay. Types of chemical bonds, or in chemical bonding, what do we expect? We expect, first of all, ionic bonds. So where we see transfer of one or more electrons from the valency shell. Okay. Then the one that donates electrons becomes positive. The other one that receives becomes negative. So we see a positive and negative ion form, giving rise to electrostatic forces between the atoms, okay, forming the bond. So because of that positivity and negativity, so there'll be that attraction. So it occurs between elements with a low ionization energy and the high electron affinity. Simply means the electrons can easily be lost by one element. The other side, the electrons can easily be gained because it requires a lot of electrons. That's an example there. Okay. So covalent bonds, there is sharing. Then there is coordinate covalent bonds where the shared electrons form a lone pair. Okay. So we'll look at all of this just to highlight. Okay. So the whole point of this bonding is in order to attain a stable configuration known as the octet rule. Okay. So you notice that I'm passing through these slides a little bit quick, a little bit fast, because we'll still discuss this. Just the highlights, what to expect to discuss. Okay. So why is the bond formed? It is in order to get more stable. Okay. So this is in order for atoms to get more stability by lowering its potential energy. So in order to do this, it has to make a bond. Okay. So because of this, there is energy liberated during formation of the chemical bonds. So what is the connection between stability and electron configuration? Noble gases have attained what we call the octet rule. So they have, some have 8 in the outermost electrons and so on. Now, every atom tries to get the octet configuration by either losing or gaining. Okay. So we'll start with the first type of bonding, or the first type of bond, the ionic bond. In the ionic bonds, so we have electrostatic force of attraction between two oppositely charged ions. So the key here is that they are oppositely charged. Okay. The ionic bond is formed due to transfer of electrons. So first of all, before we form the ionic bond, we need to transfer electrons. Once we transfer electrons, these atoms will become charged. The one that loses becomes positive. The one that gains will become negative. Okay. So the electrostatic forces of attraction are what to keep them together, because one is positive, one is negative. So there will be attraction between the two. Okay. Okay. In covalent bonds, we have sharing between two atoms. Okay. So covalent bonds are usually formed between two nonmetals. Okay. So that's about ionic bonds. Sorry, this slide, we only have one slide for ionic bonds because it's basically just between a metal and a non-metal. Here we have transfer of electrons. One becomes positive, the other one becomes negative. The other one becomes a cation, the other one becomes an anion. Are there any questions on ionic bonding? Or do we need further clarification on ionic bonds?
Yes, more clarification.
Kindly ask your question. So those who need clarity, you can ask the question and we will proceed. Okay. Since no one is asking, you ask later, we'll still get back to it. Now in covalent bonding, we have sharing. Okay. So the key here is that there's sharing, okay, of an electron pair. This is formed between two atoms of which the electronegativity difference is less than 1.7 on Pauling scale. So if you go to your textbook, you find somewhere, or you find the table which says Pauling scale. So you realize that this bonding, this covalent bond only happens if the difference in electronegativity is less than 1.7. Okay, so this is normally between non-metals. Okay, so the Lewis symbols and structure tells us how the electrons are shared. This one only shows us the outermost electron. Okay, Lewis symbol is a chemical symbol of an element surrounded by dots, which represents one of the s or p valence electrons of the atom. In short, it is only going to show us the electrons in the outermost shell, the valence electrons. Okay, these are the ones we're interested in the Lewis structure. We shall not show those in the inside, on the inside, okay? So the key here is that they are valence electrons. It is used to represent distribution of valence electrons in an atom or a molecule, okay? So if you ask to draw the Lewis structure of a certain atom, only show the valence electrons. Remember, only show the valence electrons for Lewis structures. Okay. So those asking about the notes, I'll send the notes. I'll surely send the notes, and we'll through the admin, then you get them. Okay. So example of Lewis structures for lithium, we only have one valence electron in the outermost shell. Sodium, we have one valence electron in the outermost shell. And so, yes, someone's raised their hand. Please go ahead and ask.
Yes, sir. Am I audible enough?
Yes, you are.
Yes, sir. My question about is on dative bond. Why, before we proceed?
Yes.
Don't you have anything to say about dative bonds?
About what?
Dative bonds.
Dative bonds.
That type of bonding. Yes,
okay.
That type of bonding.
So we are proceeding one bond after another.
Okay? All right, sir.
Yes.
Right.
Maybe at the end we can still revisit it, or after we discuss the covalent bonds, we can still look at the dative covalent bond. Okay.
All right. Thank you, sir.
Yes. So dative can also be coordinate covalent bonds. So it's somewhere in the slides, you'll see it. Is that okay?
Yes, sir.
Okay, thank you. So the fact of it, we see that the Lewis structure here is only showing us the valence electrons. Okay. So it is only showing us the valence electrons. Here we have a molecule, okay, where we have the two atoms. So again, here we are only going to show the valence electrons. But since there is bonding that has taken place, we are going to see this continuous line, which is representing the shared electrons. Okay. So the first arrow here okay. So the first arrow here is showing that this electron will these two electrons will be shared. So when they are shared in that covalent bond, we shall represent it with a continuous line. Then the outside will be non-bonding electrons. These are the ones which are not taking part in the covalent bond, but they are still valence electrons. They are still electrons of the outermost shell. So we need to show them. Okay. So the Lewis theory says that electrons in the outermost shell play a fundamental role in chemical bonding. Okay. So in some cases, they are transferred, resulting in positive and negative ions. Okay. That's an ionic bond. In other cases, these are shared. in covalent bonds. So since we're discussing covalent bonds, we are going to see a lot of sharing. Okay. So double bonds, for example, carbon dioxide, we see the sharing. Okay. And we can represent it in this form. The shared electrons, a single pair of shared electrons is one continuous line. There are two shared electrons we have to show. If there are two pairs of shared electrons, we shall show it with two continuous lines. Okay.
Excuse me, sir, I can't hear you.
Sorry. So in writing Lewis structures, okay, in writing Lewis structures, we follow the following steps. Okay. So we determine the total number of valence electrons in the structure. That's one. Then two, so all the atoms which are bonded, we determine this one has got so many valence electrons, this, the next atom has so many, and we calculate the total number. Then from there, we identify the central atom, the one with the lowest electronegativity, the central atom. Remember, hydrogen can never be a central atom because it can only make one bond. Then we write the skeletal structure, okay? And we join the atoms in the structure by single covalent bonds. So you start with giving a single covalent bond to each. If that happens, for each single bond formed, subtract 2 from the total number of valence electrons. So we'll see when we see a detailed representation of this, but we need to follow this stepwise. So after we have identified the central atom, and we write the other atoms in the sides or around the central atom, then we need to join the atoms in the structure by single covalent bonds first. Once you do that, for each single covalent bond that you join, you subtract 2 from the total number. Then after you do that, with the remaining valence electrons, you complete the octets of the terminal atoms. Okay? So you complete the octets of the atoms surrounding the central atom. Okay? Then the 2 extents also complete the octets also of the central atom. If at this stage the central atom lacks an octet, then you start forming multiple covalent bonds. So the next covalent bonds coming in, okay, will be because the central atom has not attained its octet state. Okay. For example, want to draw the Lewis structure of water, of H2O. So first we determine the valence electrons. The hydrogen atom has 1 valence electron. Now, since there are 2 hydrogen atoms, you have 2 valence electrons from the hydrogen. Then the oxygen has also 6 valence electrons, giving us a total of 8 valence electrons. Okay. Step 1. Step 2 and 3, we identify the central atom. Remember, hydrogen can never be the central atom. So our central atom is oxygen, or the oxygen atom, the oxygen atom. Then we join the remaining, the 2 hydrogen atoms, the oxygen, by a single bond. So this single bond here is representing 2 electrons. So from 8, we subtract 2 to remain with 6. This other single bond, we subtract 2 from 6 to remain with 4. Okay. Now, since the 2 hydrogens have attained their octets, okay, they have attained the full outermost electron. They have 4 outermost electrons, each having 2 in the outermost shell. Simply means we distribute the remaining electrons around the oxygen because the hydrogens are full. Okay. Therefore, we have 2 pairs of electrons around the oxygen. And if you count, if you put a pair of electrons here, you put a pair of electrons here and a pair of electrons down here. Okay. And you count since this line here is representing 2 electrons, you are going to have 8 electrons around this oxygen. It has attained the noble gas configuration. Okay. So, any questions on the Lewis structure? Any questions on the Lewis structure?
It's clear, sir.
Clear? What about others? Please let's discuss whatever.
Can you explain about the central atom?
Yeah, that's what I wanted to ask.
So the central atom is the one which has the least. Okay, so I'll start from here. The one with the least or the lowest electronegativity. Okay. Okay. So in this case, whenever you're given a molecule, for example, water or carbon dioxide, you look at the electronegativity, or you look at the atom which requires the most stability. Okay. Which one has the least possible? Which one is the least possible stable? I would say, or which one is most likely to gain more electrons? Okay. This bond of H2O, you cannot have hydrogen in the center because remember, hydrogen only needs 1 electron. It can only make 1 possible bond. Now, oxygen will make more bonds. Okay. So, in this case, you look for the electron or the atom, sorry, which can make more bonds. So, in this case, it was the oxygen atom.
Sir,
Yes, sir.
I noticed you said something about the central atom having been like less like.
Yes, sir. Sorry, my network was breaking.
Hello?
Yes, I can get you now.
Yeah, so like I'm behind with that statement. Can you
So I didn't get you.
clarify for me?
Okay,
Like
so
you said something like. Should I repeat my statement, sir?
yes, please. Or maybe you want me to clarify on the
Yes.
central atom.
Like on the statement that you used, you said that the central atom is the one that like it's the least with it should have a least electronegativity. That's what you said.
Yes.
If I heard correctly. Yeah. So how possible is that? Like
Okay.
looking at water,
Okay.
oxygen
So what?
is more electronegative.
Okay. So we'll start with what's the definition of electronegativity? So we are talking. You are quiet.
Oh yes, I'm listening. I muted my mic.
Oh, okay. So in this case,
Yeah.
okay, if we are comparing, we will not compare with between hydrogen and oxygen because hydrogen can only make one bond. the statement here says it is often the atom with the lowest electronegativity. Okay, and then the next point says hydrogen is never the central atom. So in this case, we have hydrogen. So that statement telling us about electronegativity rules out the possibility of having hydrogen as the central atom. That's the first thing. Secondly, if we are comparing other atoms, as we'll see later on, we'll look at the one which has the lowest electronegativity, or the one that has the least ability to attract shared electrons. Okay. Are we getting that?
Yes, sir. Thank you.
Yes. So as we move on, we get other examples where we need to compare electronegativity. But for this one, our second statement tells us that we cannot use hydrogen because it will only make one bond. Okay. So then formal charge, okay, as we are drawing these Lewis structures, okay, as we are doing Lewis structures, as we are calculating or drawing Lewis structures, you calculate what we call the formal charge, which helps us to select the correct Lewis structure. Okay, so in calculating the formal charge, we need to consider the electrons, or only consider the outermost electron. Okay, so a formal charge, it is the electrical charge, it's an electrical charge. Okay. So looking at an example of how to calculate the formal charge, so it must be as small as possible. Negative charges usually appear on most electronegative atoms, and positive charges will appear on the least electronegative atom. Okay. So the sum of formal charge needs to give us 0 if it is a neutral atom. Okay. For a neutral atom, or it should be equal to the ionic charge if it is a polyatomic ion. In short, if we draw a molecule or an ion with a charge, the formal charge of the whole molecule must be equal to that charge we've assigned to that ion. If it is neutral and has no charge on it, the formal charge must equal to 0. Okay. For example, or the formula for calculation of formal charge is number of valence electrons in an isolated atom minus the number of bonds to the atom, then minus the number of shared electrons. Okay. For example, find the formal charge of atoms in sulfuric acid structure. So the formula for sulfuric acid is, or the structure for sulfuric acid is that one we are seeing there. We have 1 sulfur, okay, 4 oxygen atoms, and 2 hydrogen atoms. So in drawing the Lewis structure for sulfuric acid, the least electronegative in this state is sulfur. That's why it is at the center. Okay. Then we complete the Lewis structure. So in on time, you can attempt this Lewis structure. You calculate the total number of valence electrons. You start distributing 1 bond to each. Okay. And you see if you can come up with this structure. So in calculating the formal charge, we'll consider the formal charge for each of these separate atoms. We'll start with the sulfur atom, okay, the S. So the formal charge will be, remember the total number of valence electrons for S will be 6 in the outermost shell. You need to have a periodic table so that you're able to see the number of atoms and so on. The atomic number and the number of electrons, okay? You write the electron configuration and you find that the number of electrons in the outermost for sulfur are 6. Then you subtract those in the ones which are bonding and the ones which are unshared. If you've seen, there's a minus on the number of bonds and the minus on the number of unshared. So we'll factor out the minus sign, and inside you have an addition. Okay. So we'll see that the 4 are the bonded ones, and the unshared, there are no unshared for sulfur. So the formal charge on the sulfur is a positive 2. We are indicating the plus because 6 minus 4 is positive 2. Do not just indicate it as 2. Okay? Then we calculate for the oxygen. So we can calculate for hydrogen. There are 2 hydrogens, so when you calculate for one, it will be equal to the other one because the bonds are similar. Number of valence electrons in hydrogen are 1. Number of shared electrons in hydrogen, 1. Number of unshared, 0. Valence formal charge for hydrogen, 0. For the hydroxyl oxygen, the oxygen bonded to the hydrogen, total number of valence electrons were 6. Those which are shared, if you look back at our diagram here, for oxygen, the one which is bonded to the hydrogen, it has how many shared electrons? It has 4 shared electrons. How many unshared? There are 2 pairs. Okay. Okay. So there are 4 shared electrons, and there are 2 shared electrons from the oxygen itself, sorry, and those 2 pairs which are unshared, giving us 4 electrons. So the 2 shared, one from the oxygen sharing with the hydrogen, and the other one from the oxygen sharing with the sulfur. So formal charge on the oxygen will be 0, the hydroxy oxygen. Then the oxygen which is not bonded to hydrogen, the number of shared, 1. The number of unshared electrons, we have 6. Okay, we go back to our structure, sorry. We have 6 unshared. Shared, we have 1. Okay, so the formal charge on this oxygen will therefore be -1. Now, since there are 2 oxygens which are not bonded to a hydrogen, we're going to have a -2 because we multiply this by 2, we multiply the hydrogen formal charge by 2, and we will also multiply the hydroxy oxygen by 2. And remember, sulfuric acid is uncharged. It is not ionic. It has no charge on itself, so it is a neutral molecule. So when you add the total formal charge here, it will give us 0. How? Remember, this -1 is for 2, so we're multiplying this one by 2. Okay, so the formal charge will be 0. Okay. Any questions on that calculation?
So can you kindly repeat on the oxygen not bonded to hydrogen?
Okay, so on the oxygen not bonded to hydrogen, how many valence electrons does oxygen have? 6. How many of these valence electrons in the sulfuric acid structure are shared? 1. How many are not shared? 6. Okay, so meaning that the 2 electrons which oxygen is bonding to on the sulfur are completely coming from there. Okay, so when we look at, if you look at your Lewis structure, you realize that the oxygen not bonded to hydrogen here has the valence electrons there. Okay, and our formal charge is telling us the pair, how many pairs are shared. So the pair which is shared on the oxygen not bonded to hydrogen is coming from the sulfur. That is why we have the 1 here. Okay, plus how many are not bonded? How many electrons? Here we're going to consider the individual electrons. Here we're considering the electron pairs. So how many electrons are not bonded? 6. The total gives us 7. 6 minus 7 gives us -1. Okay, now since there are 2 oxygen which are not bonded to hydrogen, are going to have -1 times 2, which is -2. -2 plus +2 gives us 0. Is that clear?
Yes.
Okay. All right. Any questions? Okay, you can do the same for this. You draw the Lewis structure and calculate the formal charge for each of the atoms bonded. Okay. So you note that the carbon in carbon dioxide, okay, the carbon in carbon, the carbon oxygen bond in carbon dioxide is not polar. Okay, carbon dioxide is a non-polar molecule. Why is it non-polar? Despite there being differences, a huge difference in electronegativity of giving us 1.4, the resultant electronegativity cancels because it is a linear molecule. If this molecule was at an angle, like the way water is bonded, you find that it would have been a polar molecule, it would have had partial charges. But because this is linear, this gives us no charge. Yes, sir. Please ask. Sorry, I can't get you. Network is breaking. Sorry?
Gone bad. We cannot get you clearly.
Sorry, I can.
And your network is really bad.
Oh, okay. I think it's just generally the network today where I am. Because I hope it hasn't been the same for the other slides. Is it better now?
For me, it's been okay. I think it's where he is.
Where he is, isn't it?
Yeah, I think
Yeah, the guy has bad network.
Yeah.
Okay.
Because he's skipping even as he's talking.
Let's proceed.
Here we can hear you clearly.
Okay.
Yeah, even me, I can hear you clear.
So we are saying that the resultant in carbon dioxide, the resultant charges or electronegativity gives us cancels each other. So they will